Dear students, welcome to another lecture on mechanics of solids. In this lecture, we are going to continue with our discussions on shear force and bending moment diagram. We will be dealing with three cases today. First one is a cantilever beam subjected to a concentrated load at its free end. So if you look, this is having a uniform loading between A and B. So therefore, we only need to consider one single region. So the number of region we need to consider is only the region AB, and we have to develop expressions for shear force and bending moment for the region AB. So what we can do is we have to consider a section XX, and we will be considering it at a distance x from the free end. So if you try to draw the free body diagram of the region to the left, so if you we know that the reactions that we are going to have at the this end would be, we will be having the shear force here, and we also be having the bending moment here. Therefore we are going to have two forces coming here, and therefore it is always better to consider the free body diagram of the section to the right of the beam in case of a right of the section in case of a cantilever beam. So let us try to draw the free body diagram here. Let us draw it here. So this is the beam, so let us call this as B, and this is your section XX. Okay, and we have the load W here. The distance here is also X, and we need to draw the positive directions of shear force and bending moment. And once again, how do we do that? You consider this as your element, and draw an enlarged view of the element here, and we know the positive directions of bending moment and shear force goes like this, and the face that we are considering is this one, which is same as this one. So we will be taking these directions as the positive directions. So this will be our Vx, and this would be our Mx. Now to calculate the value of Vx and Mx, if you go for sigma Fy equal to 0, what we will be getting is, we will be getting Vx equal to W. This will be the expression for shear force, and if you go for sigma Mx, M about the section XX equal to 0, we will be getting Mx plus W into X equal to 0. We will get Mx equal to minus Wx. So these are the expressions that we have. Okay, so once we have the expressions, we only have a single region. We have the expression for Mx as well as Vx. Now what we will do is, let us draw the tabular column. So in the tabular column, the region that we are having is only a single region AB, and in addition to that, we require the origin. The origin is B. Next thing is, we need expression for the bending moment. The expression for bending moment is minus Wx, and we need expression for shear force. The expression for shear force is plus W. Okay, so once we have this, we are ready to draw the shear force and bending moment diagram. This is W. Let us draw the shear force diagram. Shear force diagram is plus W. So in the entire region, what you're going to have is, you're going to have something like this. When we say this plus W, it is a constant. W is a constant. dV by dx equal to 0, which means it is a horizontal line. And at x is equal to 0 as well as at x is equal to L, it is going to have the same value throughout. So you can draw it like this. So this will be plus W. This will be your shear force diagram. To draw the bending moment diagram, what we have to do is, the expression is minus Wx, that is y is equal to mx plus c. It represents a straight line, linear variation. At x is equal to mb is when x equal to 0. So we'll get the value of mb as 0. And at a, x equal to L, so to find ma, x is equal to L, if you substitute, you will get it as minus WL. So this is minus WL, and this is 0, and you join it by a straight line, WL. This forms the bending moment diagram. Okay, so this is how we draw shear force and bending moment diagram for a cantilever beam subjected to concentrated loading at the free end. Next question that we have to consider is the case of a cantilever beam subjected to a uniformly distributed load. Okay, so here again the loading is uniform in the region AB, and we only need to consider a single section. So what we will do is, again we will consider section XX at a distance x from the free end. If we try to draw the free body diagram, the free body diagram is going to be like this. So this is your XX, and as we know, the face that we have to consider is this one. So this would be Vx and this would be Mx. If you go for equilibrium, okay, we will get Vx is equal to Wx, that is Fy equal to 0. If you go for sigma Mx equal to 0, we will get Mx minus Wx is the resultant acting at x by 2 equal to 0. We will get Mx equal to minus Wx square divided by 2. So these are the two expressions for shear force and bending moment. So once we have expressions for shear force and bending moment, what we have to do is we need to form the tabular form. So the region is AB, we require the origin is B, we require expression for Mx minus Wx square by 2, we require expression for Vx, expression for Vx is Wx. How do we draw it? This is y is equal to mx plus c. Shear force is a straight line. At VB, x equal to 0, it's 0. At A, x is equal to L, it is WL. So what we are going to have as the shear force diagram is going to be a straight line. It is 0 here, it is WL here. If you have 2 points, you can join a straight line. Value is WL, it is positive. Next is to draw the bending moment diagram. We have the expressions. We need to find it at B. At B, x is equal to 0. If you substitute, you will get MB is equal to 0. And at A, we have x is equal to L. If you substitute, you will get it as minus WL square by 2. And again, if you look, what we are having is a quadratic variation, that is ax square plus bx plus c. And if you look, we have a negative sign. It means that it is going to be a negative parabola. So basically, what we are going to have is the diagram would be something like this. It is going to be an inverse parabola. Okay, so it is going to be an inverse parabola, and the magnitude here will be WL square by 2. So this will be the bending moment diagram, and this would be the shear force diagram. I hope this idea is clear. So basically, this is the parabola, and if you take this side alone, that is what you call as the inverse parabola. Okay, inverse parabola is nothing but a part of the parabola. Okay, so if you draw it like this, then this is your inverse parabola. If you draw it the other way, it becomes your parabola. Okay, so this is our shear force and bending moment diagram for a beam subjected to cantilever beam subjected to uniformly distributed loading. The next case we have to consider is the case of an overhanging beam. So let us consider the last case, which is a beam with overhang. Let us say we have a load W here. Let A be the overhang and let this length be L. So first step we have to do is we need to find out what are the different support reactions. So how do we find the support reactions? Let us find out the support reactions one by one. So if we draw the reactions, this will be the reactions, this will be RA, and this will be RB, and this would be W, this would be A, this would be L. If you take sigma m about B equal to 0, so RA into L is equal to W into A, so you will get RA equals WA divided by L. Okay, so RA is WA divided by L. So if RA is WA divided by L, then we have RA plus RB is equal to W. So RB is equal to W minus WA divided by L. So this is W into 1 minus A divided by L. Or you may rewrite it as W into L minus A divided by L. So this will be the expression for RB. So we have multiple expressions for RA as well as RB. Now what we have to do is we need to draw the shear force and bending moment diagram for this beam. Again, if we look, there are three concentrated loads in this particular figure. That means the entire region of the beam can be divided into two regions of uh, uniform loading. One is the region AB and another is the region BC. So let us try to consider the different regions of the beam. So this is A, this is B, and this is C. So if we consider the region AB, let us consider a section XX at a distance x from here. And if we consider the region BC, let us consider another section XX at a distance x from C. Okay, so for the region, let us consider the region AB first. Let us consider the free body diagram to the left of the section. This is WA by L, and this is our section XX. So we have the sign conventions here, and we have to choose. This is what we are having, and we have to choose this directions. So what we are going to have is this will be Vx and this will be Mx. So if you simplify this equation, we'll get Vx as WA by L, and if we further simplify, we'll take the moment equilibrium, we'll get Mx as WA into X by L. Okay, so this will be our expressions for shear force and bending moment in the region AB. In a similar fashion, let us also try to take the free body diagram of the region CB. Okay, if you consider CB, this is your section XX, and this is the distance X, and we are having a load W here, and again we have to take the positive directions. And in this case, if you look, this is the side that we are having, we will be taking these directions. So if you draw the directions, this will be Vx and this will be Mx. If you write the equilibrium, apply equilibrium equations, we will get Vx is equal to W, and we will also get Mx is equal to Wx. Okay, so Mx is equal to minus Wx, we will get Mx equals minus Wx. So these will be the expressions for the region CB. So once we are having developed the equations for AB and CB, what we have to do is we have to draw the tabulation. So in the tabulation, we have the region that is AB, another region is CB, Next thing is the origin. Here A is the origin and here the origin was C. Next thing we have is expressions for Vx. So if you look into the expressions for Vx, first one was Wa by L and the second one was W. Okay, so this was Wa by L and this is W. And the expression for Mx, if you look, the expression for Mx is Wax by L and this was minus Wx. So these are the expressions that we have. So having these expressions in a tabulated form, we are now ready to draw the shear force and bending moment diagram. Okay, so what we need is, let us take Vx. So to draw Vx, what do we have to do? We require we need to know what is going to be the nature of variation. We also need to know what are the values at the salient points. So at the point A, as A is a constant, W is a constant, L is a constant, this value is a constant. So in the region Vx, in the region AB, it is going to have a value Wa by L, which is positive. Also, one more thing we have to notice is the value of Vx. Mm, okay. So this is what we are having. And in this region it is W. So this is W here. Shear force is W here and shear force is W A by L here. So if we go here, this will be the shear force. Okay, so it is W in the region BC and it is WA by L in the region, in this particular region. Now what we have to do is, next thing we have to do is, let us try to draw the bending moment diagram. So to draw the bending moment diagram, at the region A, x is equal to 0, the bending moment diagram is 0, and at C, x is equal to L, we will get bending moment as WA. Okay, this will be WA, and if we consider from the other side, at the point C, the bending moment is 0, and at the point B, if we look, x is equal to A. So if we substitute, we will get MB as minus WA. Okay, I think there is some mistake in the expression for bending moment. Mm, this reaction has to be in the downward direction. Okay, this reaction has to be written in the downward direction. So that is the mistake. This is in the downward direction, and therefore we will have a negative sign coming here, as well as a negative sign that is going to come here. Okay. So we will be having a negative sign here as well as a negative sign here. So maybe we'll draw it again. So to get the shear force, at A the shear force is minus WA by L. So how do we draw it? It is minus WA by L, and this is minus WA by L, and at this point it is W. So we can mark it as W here, and it is positive. So all we have to do is join them like this. So this will be the shear force diagram. Now bending moment at A, x is equal to 0, bending moment is 0. At B, x is equal to L, bending moment becomes minus WA. If you are considering this equation, at C, bending moment is 0, and at B, x is equal to A. So if you substitute, we'll get minus WA. So all that we have to do is, it is going to be a linear variation, and this will be the variation that we are going to have. This is WA, it is going to be minus WA. So this will be the bending moment diagram that we are going to have in this particular case. Okay, so this is how we develop shear force and bending moment diagrams for cantilever beams. Again, if we want the deflected shape, the deflected shape is going to be something like this. Okay, we are going to have the entire region of the beam hog. Okay, so with this we are going to stop our discussions on shear force and bending moment diagram for simple cases, and in the next lecture we will be dealing with beams beam span having multiple loadings. Okay, there will be multiple loading on the span, and we will see how to do shear force and bending moment diagram for such cases.